Hello everyone. Today I am again with you with the video lecture on the topic subgroup. So we will understand what is the definition of subgroup. So let G with respect to binary operation star be a group. Be a group. And you know the properties to be satisfied for a non-empty set to be group is closure axiom, closure property. Number 2, associativity. Number 3, existence of identity. Number 4, existence of inverse. These 4 properties are to be satisfied for any non-empty set to be group with respect to binary operation star. So firstly we have supposed that G be a group satisfying all these 4 properties, and H non-empty subset of G. Here look, this means non-empty, and H is subset of G. Then H is set to form subgroup of G if H with respect to binary operation star is itself a group. And we know H will be group, then H with respect to binary operation will be satisfying all these 4 properties. Okay, besides that H has to be non-empty and it has to be subset of G. If these conditions are satisfied, then we say that H, which is a subset of G, forms subgroup of G. We will study it through an example. So example we are taking is, let G be set of integers. So it will be having elements 0, 1, 2, 3 and so on, and in the negative side -1, -2, -3 up to minus infinity, and H is equal to twice of Z, so that is even integers 0, 2, 4, 6 and so on, -2, -4, -6 and up to minus infinity. Now we shall prove that H is subgroup of G. For this, firstly we know Z under binary operation addition is a group. Next we have to prove H is subgroup. So firstly see whether H is non-empty. Yes, H is non-empty because it is having so many elements. So for a group to be non-empty, existence of single element is more than enough. So therefore H is non-empty. And since H is set of even integers and G is set of integers, therefore clearly H is subset of G, because G is having more element, H is having the same element as that of G but lesser in numbers, only even numbers. So this implies that non-empty, H is non-empty and subset of G. So first condition is satisfied. Now next we prove that, next we show that H with respect to addition is a group. For group we know that first property is closure property, so we will see closure property. Let A and B are two elements of H, and elements of R of H are of the form even integers, and we know that sum of two even integer is again an even integer, so this implies that A plus B will also be in H. Therefore closure property is satisfied. Number 2, associativity. Let A, B, C be three elements of H. This implies that if we add three elements, and firstly we add B and C, then result to add to A, then we that this result is equal to C, and this is holding for all A, B, C belonging to H, because we know that if we have the integers 2, 4, 6, if we add these two, result is 12, and if we add these two first, result is again 12. Therefore we can say that 2 plus 4 plus 6 is equal to 2 plus 4 plus 6. So this is associativity with respect to addition. Now next we see the existence of identity. Associativity is proved. Next we see the existence of identity. Number 3, existence of identity. In a group of integers, we know that identity is 0 with respect to addition. As we know that H is subset of G, and 0 is also there, so the property which is holding for every element of G will also be holding for every element of H also, because it is a subset. So we can say that there exists 0 belonging to H such that A plus 0 is equal to 0 plus A is equal to A, and that is for all even integers belonging to H. This implies that E is equal to 0 is the identity of H. So the third property is also satisfied, that is the existence of identity. Next we shall see existence of inverse. Fourth one, existence of we know that for G there is inverse of every element. Okay, so inverse is existing for G, as G is a group, so that will also hold for elements of H also. Let us see elements of H. If I again rewrite, are 0, 2, 4, 6 and so on, minus 2, minus 4 and so on. For 2 there is minus 2 which is added to 2 gives 0, which is the identity, and for minus 2 there is 2 which is added to 0 gives identity. So for every element there is the negative of that, which is when added gives to 0 identity. Therefore for every A belonging to H, there exists minus A belonging to H such that A plus minus A is equal to minus A plus A is equal to 0, which is nothing but equal to identity. Therefore, B is equal to minus A is the inverse element for A belonging to H. Therefore, inverse of each and every element for each and every element exists. So fourth property is also satisfied. Therefore, all the four properties have been satisfied by H. Closure property satisfied. Sum of two even integer is again even integer. Associativity is satisfied. Existence of identity 0. Existence of inverse negative of any number or minus of that number is the inverse. So all the four properties are satisfied. Therefore, there is no exaggeration in saying that H with respect to binary operation plus forms a group and it is non-empty subset of G. This implies that H with respect to binary operation addition is a subgroup of G plus. So this is I have from the definition of subgroup, and that we have also given an example. So one question I am giving you as an exercise, and you will try it and will send me the solution, that how to prove this as a subgroup. Let this is exercise. Let G is equal to 1 minus 1 iota minus iota be a group with respect to multiplication, and H is equal to 1 minus 1 is subset of G, then prove that H is subgroup of G. This is important question. So this is all I have from this lecture, where we have discussed the definition of subgroup and also taken an example and illustrated that how it forms the group, and I have given you a question as an exercise. Very soon I will be with you with my next lecture on subgroups, where we will be taking an important theorem. So this is all I have from this lecture. If you like the video, please like, subscribe, share and comment. This is Dr. Rajesh saying you goodbye. Thank you for watching.